Hello everyone, welcome to High Performance Computing, Advanced Scientific Computing. This is lecture 8, Computational Flight Dynamics. Let me introduce myself before starting this lecture. I'm Reza, a postdoctoral researcher at the University of Iceland, currently working with Moore's Research Group. My focus on the turbulent flow in the fluid dynamic, and I am applying the HPC, AI methods, and CFD in this area. It's my pleasure to be on this course, and I will take over the second part of the course from lecture 8 to lecture 15. This year, I need to mention that because of the time and Easter break is approaching, and also it's planned to students have a final project with the industry. So we managed to have your lecture time focusing mostly on the project, working with your teammates. Then from this lecture, we will have a shorter presentation for each lecture to cover the material of the course, and also you're able to work on your final project. Now let's continue for this lecture. Let's first have the review of lecture 7, distributed deep learning and application. As it's discussed in the lecture 7, because of the deep learning model, it's developing and growing fast. There are two matters, the size of the data and also about the models, the deep learning model and their parameter. So for the distributed deep learning, in fact, there are two options we can do. We can distribute the data between different number of the nodes, and then each node have a copy of the deep learning model and running the training for this type of the deep learning. And the other one, when we have a complex and a very high number of the parameter of the deep learning, we can distribute the deep learning model between different nodes. So in fact, this approach is important to be able benefit from the parallel computing for deep learning model. Since size of the data and number of the parameter and complexity of the deep learning model is growing, this action is in the complex cases is required. Here we have outline of the course, which this year it's planned to have a CFD special. On the lecture 8, we will start for the introduction for the CFD. And now let's begin. These are the subject it will cover in this short lecture about the CFD and its background, range of its application. We will talk shortly about the Navier-Stokes equation, what are the schemes it's using in the numerical method, some point about the meshing and boundary condition, and the three categories that it's used in the CFD for turbulent flow. Computational flight dynamics, which is called CFD. CFD is a numerical method which is used in the fluid dynamic. Regarding the fluid dynamic, there are evidence that it show has a very old history. One of the key figures, for example, was Archimedes. It was at the time before Christ, and he designed and used the fundamental of the fluid mechanics in some inventions, like the water screw, which transport the water and granular material. To study the fluid dynamics, usually there are three approaches. One of them is experimental, which it's showing the much more evidence in this area. Then we have the theoretical and analytical approach, and the other one is the numerical approach, which is relevant to the CFD. In this slide, you can see example from the fundamental of the uh, fluid dynamic in some invention and application. There is a drawing from the Leonardo da Vinci, and also there are examples from the wind turbine from very old time. Now let's see what's the computational fluid dynamics. In fact, when we are dealing with fluid dynamic problem, we will talk much more about the complexity of the equation, the governing equation, and the boundary condition and initial condition, how it's impacting the problem in the fluid dynamic. Then when we are dealing in such problem, maybe we have a governing equation, but because of the complexity of the problem, non-linear term, and also some limitation and unknown issue about the initial condition or boundary condition, it's difficult to have an analytical solution for it. In the CFD, the approach is making very small grid point on the problem domain and using this scheme to solve the problem point by point or element by element. There are very different approach in this method. One of them the finite difference, one of them finite volume method, and one of them is the finite volume method. Each of these method has its drawback and capability, and depend of the project, depend of the geometry of the problem, depend of the boundary or initial condition. Uh, the expert decide to use which of these approach. So here in this slide, you can see example of a problem at how it's discretized to very small element, and then using the finite difference method to find and solve the problem for the target properties, like could be velocity, pressure, or for example in the heat transfer it should be the temperature. And this approach in fact has a great power. However, from the turbulent flow and the fluid dynamic, the big issue is we don't have enough understanding that how the processing of the turbulence is happening. But the CFD helping us to solve the problem and to get the solution. That's why in the industry, it has a lot of application, and we will point to some of its application. Now let's see what we are using the CFD. To analyze the fluid dynamic problem, as we mentioned in the history section, there are three different perspectives. One of them experiment, the other one analytical solution, and the third one is the numerical solution, which is relevant to the CFD. The experiment possible to conducted with a specific problem. There is a limitation for the measurement. For example, when we have high temperature or we need very specific initial condition or boundary condition for problem, maybe we can't perform it in the controlled laboratory condition. The tools and the cost of the experiment, it's a matter. And there is an issue about the scaling also about the experiment. How the experiment helping us to validate the numerical solution. The analytical solution is available limited for the limited number of the problems, especially only when they are linear. For the nonlinear, it's very complicated. For the about the computation also sometimes is very costly, and for most of the problem there is no analytical solution. And it's great that it's presenting general solution equation for the problem. Now let's see what about the numerical solution and the CFD. It doesn't has limitation for the solving. Uh, also, it's possible to reduce the computational operation cost, depend on the method. It could be used for the complex problem, depend on the geometry also, and maybe the boundaries. It could be validated before the application. However, on the CFD, we need to have the boundary condition, initial condition, and the computation time also is depend to the power of the computer. This term exactly what we will talk about it in this lecture and in this course, and we will see how the HPC placed on the high critical part of the CFD when we are dealing with complex problem with turbulent flow. It's required to have the HPC to able to solve this problem. And of course, the HPC development accelerate the solution for such a complex problem in recent years. When we are dealing with the CFD, we have equation which they are governing equation for the problem, and they are partial differential equation. We call them PDEs. When discretizing the domain of the problem to the small grid, which could be element or grid points, these PDEs equation will be converted to algebraic equation, and then the computer power could be used to solve these such uh, equation. In fact, to have the governing equation, the fluid dynamic, we have the mass equation, continuity, momentum equation, energy equation, and these three equation it's led to the main equation. The fluid dynamic is called Navier-Stokes equation. Here it's some link for the example of the material for application of the CFD, which are very important and in the development of some achievement, for example, from NASA. And there are some examples from software also can be seen here. And if you are interested, you can look at them. For the CFD application also, there are different categories of the code. We have some commercial code like ANSYS Fluent, applied computation fluid dynamic, also fluid dyne, and etc. Also, there are some open source or free codes like OpenFOAM, Calculix, CANS, Dolphin, FluidSim, and else. It depends to the requirement and what type of the problem we need, or it's for the research or it's for the industry. We are using the relevant code. The open source code it's a great opportunity and it's possible to have your new code and add it to these sources and solve this kind of problem. In fact, the CFD code also includes grid generation or meshing and solving the problem and the visualization uh, to able to see the solution and how the problem is behave based of the designed boundary and initial condition. Um, for most of the CFD code that's are available, basically they are packaged that to dealing with the simple problem, but they are capable and designed to handle the complex geometries and industrial problem. Here we have listed some of the uh, well-known sources, open sources for the code, like OpenFOAM, as I mentioned, Alia, ABBP, and Basilisk. Also, Maya, they are from the different institution and university in the Europe, and they use for the complexity of the turbulent flow. Uh, and we will talk much more in the next slide about the turbulent flow and why it's matter, and why the CFD is very important in the area, with the requirement of the high performance computing. Regarding the CFD, usually it's assumed as a multidisciplinary topic. Here it's nice presentation. For the CFD, as we can see, the knowledge of some of the fluid mechanics, it's required numerical analysis and computer science to perform the great solution for the complex CFD problem, which is required the computation. In fact, the CFD, it's in the traditional application, have been one of the most demanding computational application, and in the sense of these requirement, it's one of the effective application which led to the development of the powerful computers. Uh, for example, it was first a single processor computer, and then in the 80 was a vector computer, then in 90 the parallel computer, and now we are talking about the shared memory and distributed memory. And you have the lecture for these different categories. So as we said in the CFD, we have guiding equation, which is basically it's from the Navier-Stokes equation. It's converted to algebraic equation, and then using the power of the computation to solve this kind of a problem. The Navier-Stokes equation, it's for Newtonian fluid and incompressible flow. It's they are in fact second order nonlinear PDEs, and here we mention it's quite formidable. To mention the complexity, here there is a presentation in these small figures for two regime of the flow or type of the flow. It's called laminar flow and turbulent flow. For the laminar flow, which in the upper one, we can see this line, it's presenting the streamline of the flow. And we can see they have a very clear motion and pattern, and we can follow these lines. But when we're looking at the turbulent type of turbulent flow, in the second figure, we can see they have a very uh, non-linearity and randomness. Uh, and when there are a lot of flow streamlines, it's very difficult to be able to follow each one. This is the complexity of the turbulent flow, which is available as a term in the Navier-Stokes equation, and it makes it difficult to deal with this kind of a problem. Turbulent flow is one of the unsolved problems in the physics now, and there are a lot of research ongoing on this area. CFD helping to solve this kind of problem in the industry. However, about the comprehensive understanding about the coherent structure and how it's processing the turbulent or still there are many unknowns. Regarding the CFD, the numerical method, it's finite difference, finite volume, finite element, a spectral method, boundary element, reduced method, and some many other new approaches. And solving these complexity with this method, it's required the computation from the high performance computing to able to get the solution and to get the result from such complex uh, domain of the problem. In fact, the equation has four unknown: pressure and three component of the velocity. And then it should be combined with the Navier-Stokes equation should be combined with the incompressible continuity to form equation for this four unknown. The Navier-Stokes equation have only limited number of the known analytical solutions. However, the CFD in recent years is provided great possibility to solve this kind of the problem and this equation in some cases. However, when we are dealing with complex geometry and three dimension, the number of the computation is increasing extensively, and then it's required to have HPC to able to solve this kind of problems. To present some matter in the CFD, here we'll mention some point regarding the meshing and also the boundary condition. In fact, CFD it's alone is a course, and it has a basic and advanced level of the courses, and the expert in this area need to be familiar with its fundamental and enough knowledge to use it. Here we are presenting it as a case which requires the HPC, and of course this lecture does not cover the whole information, whole required material for the CFD expert. However, if you are interested, there are a lot of references with example, and you can look at them and you can see how the governing equation is uh, created based off the problem, and then defining the initial condition or boundary condition, and then select the relevant method to solve this type of the problem. Here, for example, we're mentioning about the finite difference method is the simple and straightforward to apply, but usually it could be used for the regular grid. In fact, for the meshing of the problem, we have structured and unstructured. You can see here in this figure how the structured one it look like and how the unstructured one. In fact, because of the some geometry of the problem, we need on some areas of the domain, we need much more fine grid to able get the correct solution. When we increasing the number of the grid, or when we are reducing the size of the grid, then the computation gets much more high. Furthermore, there are limits also that how much we can make the grid smaller and teeny, and this is the base of the knowledge that you have from the problem, and also about the limit and some point that you need to meet in your problem design. The other one is finite volume method. Usually it's used for the irregular meshes grid. So when we have meshes which they are not in the usual form, we can use the finite volume method. The other was the finite element method, which is, this one is the much has a much more power than others. It's working for structure and structure grid. However, from the mathematics views, it's much more complex than other two, and it has a sophisticated computation. Uh, and but it's able to solve any problem with different equation, and it's known as a complex method. For example, most of the commercial software, the CFD, they are using the finite volume method. The finite element method also is available, and it's able to cover much more complex problem. In the fluid dynamic, we have a type of the flow, or we call it flow regime, which is called laminar flow and turbulent flow. To have a visualization of these two different regimes, here we are presenting the flow passing a cylinder. The upper one is turbulent flow, and the second one is the laminar. We can see when the flow in the laminar regime passing a cylinder, it has a symmetric around this object, and it's very easy to follow or maybe predict the flow. And for the laminar flow, we are able to solving the analytical solution for it. But when we are dealing with turbulent flow, as we can see, when flow is passing the object, this cylinder, there is a wake and complexity geometry for the flow uh, in the downstream when it's passing the flow, passing the object. And this complexity could be seen in the solution and dealing with the analytical solution for this kind of the problem. To categorize this flow regime, there is a non-dimensional parameter. It's called Reynolds number, which is defined as the inertial force to the viscous force, which is mean in the turbulent flow, the inertial force will be dominant in the flow. And when these power of the inertial reducing, then we have the laminar flow. Therefore, the Reynolds number has a range, depend on the type of the problem and the boundary condition of the problem. For example, when we have internal flow, like pipe flow in the pipe, there is a specific range for the flow when it's laminar and when it's turbulent. And in fact, between these two regimes, there is a unstable area. It's called transition area when the flow is transitions from the laminar to the turbulent flow. This has also a specific range. In this area, the flow is not turbulent and not laminar, and it's between them. Then the flow reaching the, if we wanna explain what's happening in the beginning, if it's laminar and the Reynolds number is increased, then the transition is happening from the transmission is transferred to the turbulent, and then it's reaching the developed turbulent flow. Here also the presentation from the flow from the pipe, how it's look like when it's laminar and when it's turbulent. And the Reynolds number, it's defining the uh, regime of the flow based on these definition. Moreover, in the fluid dynamic, we have categories of the compressible and incompressible flow. In fact, it's leading to another non-dimensional number. It's called Mach number. Uh, when we have the fluid dynamic, the compressible flow mostly about the gas dynamic. And when we are dealing with the hydrodynamic and incompressible aerodynamic, which Mach number less than one, we can say it's incompressible flow. The behavior of these flow is completely different, and we can say the experts that are working in these two areas. They are specialists in the compressible flow or incompressible flow. And it's required its knowledge to be used. In fact, the behavior of the gas and the liquid is different, so it's required different method of the solution, and also regarding the governing equation when it's used and how we behave with them when we are using the CFD to solve this kind of problems. Uh, just to have a short stepwise of a CFD application on the PDEs. In fact, for the PDEs, there is a classification. It's called the PDEs could be hyperbolic, parabolic, or elliptic. And to solve this kind of the equation, the boundary condition and the initial condition required in different way. Some of them need both of them, some need one of them. However, for example, in the finite difference method, when it's used, it's very important to have the scheme for the solution to have a consistency, stability, and convergence, which they are three factors. It needs to be checked when we are using the CFD to solving a problem. To stepwise the problem solution in the CFD, first we have the physical knowledge of the problem, then physical model. And then we need to have the governing equation of the model of the problem, defining the boundary condition, initial condition. Then the discretization it's need to be done, which is led to the meshing. In fact, in the software, we will obtain the system of algebraic equation. And then here the numerical method is come to solve this type of problem. Is depend of type of the equation and solving by computer, and then doing the post processing and the visualization. Uh, Here in this slide, you can see how the grid point is generated for the finite difference method. There is a domain of the problem, and it's discretized to the small uh, grid mesh with the size of the in two-dimension size, delta y and delta x. This size of these element also is required to be checked to have the consistency and stability of the solution, and then be sure that this solution will converge to a right solution. Uh, in fact, as we mentioned, this type of the method, the finite difference, of course, is limited and doesn't has capabilities similar to finite element method or finite variable method, especially about the geometry. As you can see, we need a structured mesh to use this method. When we creating the algebraic equation in the CFD, it depends to the setup of the problem. Usually when we are dealing with the unsteady problem, which is changing during the time, we will have explicit type of the problem, which is mean we have one unknown, or implicit, which is mean more than one unknown problem. As we mentioned in the finite difference, we need to have the consistency, stability, and convergence. There are different known methods, for example, in the finite difference method to lead to explicit or implicit method. In the explicit one, for example, we have the forward time central space, which is conditionally stable. But we have the default Frankel scheme, which is unconditionally stable. About the implicit method, the Lassonon scheme and Krank-Nicolson scheme are implicit method. When we categorize these different scheme to explicit and implicit, here the important point is coming about the HPC. When we are using the implicit method, mostly they have great stability because more than from other view, because more than one unknown appear in the algebraic equation, then more computation time is required per step. So here the HPC is required to perform it faster. And sometimes if we don't have enough computation, we are not able to solve this kind of problem. Then using the implicit method leading to much better solution, stability, consistency, and convergence. We mentioned two examples of them, Lassonon and Crank-Nicolson, but much more computation is required. Some point about the HPC, the grid size and time step both directly affect the stability and consistency. It's mean when we have a smaller time step and smaller grid size, we can have much more stability and consistency. However, with limit, and we need to know this limit. But when we have a small size, fine size of the grid, and also small time step, it means we need much more computing. Then it means when we are using the setup to have much more stability and consistency, the computing required higher. Then the time step and grid size impact the computation time, especially when we are dealing with three dimensions. We must choose grid size and time step to meet a stability condition and perform suitable computation time. Then it's very important that uh, when we need to solve some kind of the problem to have enough uh, computation power. Regarding the scheme to solving them, for algebraic equation, we have two different main approach: direct method and iterative methods. For example, for the low upper decomposition, Gaussian elimination, matrix scaling, and Gauss-Jordan elimination, we are using direct method. The iterative method is using for Jacobi, Gaussian Seidel method, and successive or relaxation SOR. For the triangular matrix algorithm, also the Thomas algorithm is available for this kind of the problem. And of course, it requires the knowledge which one need to be selected depend of the scheme and the problem. As we mentioned before, when we are dealing with unstructured, we need to use the other method like a finite volume and finite element method. In the finite volume, we have grid and uh, element uh, for 2 dimension and 3 dimension. Here you can see some of them, and we need to use this shape of the grid and volume to discretize the domain of the problem for unstructured one to be able to solve this kind of the problem. Which make the complexity much more because sometimes we don't have symmetric geometry, and it's make much more computing required. And also we have different sizes of the element, and they are not all in the same size. Then so far here we saw some point that it show how the CFD solution is getting to the high competition, and we need the HPC to solve this kind of the problems. And if we want to be much more detailed about the competition, rather than the number of the elements, size of the element, size of the time step, then when we are dealing with turbulent flow, which in the fluid dynamic, in fact, most of the flow is turbulent, especially in the industry, and most of the phenomena that we can see. Then the majority of the fluid flow is turbulent. In the turbulent flow, there is a broad range of the scales and high dimensionality with non-linear interaction. Uh, and there is a point also, it's sensitive to initial condition. In fact, in the initial condition, usually there is a perturbation, and always from the view of the experiment, for example, if we are performing experiment with a similar setup, every time when we run this experiment, we will never get the same condition of the performed experiment. Uh, in fact, they are in the same range when they're similar, but the initial condition very sensitive to the perturbation. And the turbulent flow, complex and randomness. When we are looking to the turbulent flow, in the mean of the flow, we can see some predictable and repeatable properties. In the turbulent flow and CFD application, there are 3 main categories. It's called Reynolds average numeric RANS, large eddy simulation LES, and direct numerical simulation DNS. We will talk in detail in the next lecture about them. However, here just we want to mention the difference in the computation for these approaches. In fact, DNS providing the most accurate solution. LES, it's in the balance, which is providing better solution, but uh, better solution than RANS, but is cheaper than the DNS, because DNS the most accurate and costly solution in the CFD. But the advance, which is mostly providing the average solution, it's a cheaper one and broadly used in the industry currently. When we look at the computation for it, usually the advance it's uh, 10 power 5 times cheaper than the LES. So it's not some cost that we can neglect it, and it's high difference in the computation. However, advanced has some limitation. For example, for some specific geometry, some boundary condition it doesn't work properly. And when we use LES or advanced or DNS, is need to have the knowledge. However, because of the computation cost, DNS it's so difficult to be used to have the required computation. And LES and advanced the most application uh, in the research and in the industry. However, the industry prefer to use the advanced. If there is an issue that could not be covered advanced, maybe they're using the LES. Here in this slide, you can see presentation of the solution of these three approaches, advanced, LES, and DNS. We can see the advanced presenting uh, average solution for this case, which is predicting a turbulence of the jet. The middle one is the LES, large eddy simulation, and the uh, left-hand side one is the DNS. And you can see how much detailed difference between DNS and advanced. However, it depends to the application and how much detail it's required from the solution. Uh, they selecting to using the DNS, LES, or as we said. LES is working with complex geometry and is cheaper than DNS, but RANS is working much more general for the regular problems. Then when we are dealing with complex problem and we need the detail of the problem, for example, and it's important for us, or maybe advanced doesn't able to solve this type of problem, it's required to use the LES and DNS, and here the HPC is the most important part which is required. However, advanced also it's required the HPC, but it's much more cheaper than two others. Let's have example of the parallel computing in the CFD for turbulent flow. Usually we can calculate the number of degree of the freedom of the problems with Reynolds number, and the Reynolds number also is in the real life most of the time is exceed 10 to 6. Then the number of degree of freedom we expect it usually 10 to 13. So it's the high degree of the freedom. If we're looking at the computer processing speed, uh, flop point operation per second, we can assume how the computation is going f over t time, clock time in second. Then this is the processing speed for this kind of the problem. Now, if we're looking on the regular calculation, the CFD with nanosecond, which is regular, and however now we are reaching the exascale, then we can expect much more computing possible. But with the nanosecond, the theoretical peak speed for this kind of the CFD problem with the Reynolds 10 to 6, which have 10 to 13 degree of freedom, then each degree of freedom take 300 flop in a single time step. These mean 10 to 6 million gigaflop per second is required. It's about a year to compute just a single time step with the power of the nanosecond or gigaflop per second. This is just example of the computation that how we need supercomputer, we need the parallel computing, we need to split the domain of the problem to a small subdomain and split them between different processor or GPUs at this time. As we know, the GPU accelerates the computation to be able to deal the computation of this type of the problem. Then we can say in this era, at this era that we are working with the CFD, the HPC is the essential part to dealing with this complex problem that we are using in many applications. Regarding the domain decomposition in parallel computing, here it's very simple example of the heat transfer example. You can see we have a two-dimension domain. And actually, we need to solve this problem with very large grid, which is mean it has 20,000 by 20,000 grid. Then the grid point are 400,000, and here you can see the number of the node per each one, and bits per number, how much mm, storage is required for this kind of the problem is 6.4 gigabyte for this problem. And you can see how it's this discretization of the domain is split to six subdomain to have a parallel computation for this domain. For the when the domain of a problem is split to a number of the subdomain, the boundary of this subdomain also is a matter because every time since from this boundary each subdomain relevant to other, they need to have interaction and change the information between each other. So this is the matter that is required in the setup and solution of this kind of problem, taking the consideration. This is so this is just a simple example to see how we can make a decomposition of the domain in the parallel computing. Then here we ended with lecture 8 from high performance computing course, and there is a video here. It's showing how we need to use the HPC for the CFD, and recently development of the cloud application of the HPC could help us in the CFD, and I suggest you to watch this video. So we will continue in next lecture uh, about the complexity of the turbulent flow and how it's helping with the HPC to deal with the complexity of the fluid dynamics. Thank you.